All right, I'm gonna show you real quickly Kepler's laws. So this is an extension of what we did the other day with the universal law of gravity. Kepler was a guy that came after Newton and was more interested in the shapes of these orbits, not so much the strength, but the path of the planets was really what he was focused on. And he has three laws. The first one's called the law of ellipses. Essentially, let me zoom out here a little bit. Essentially, these planets do not go in perfect circles. They are ellipses, which means they have two center points, and the planet will orbit around the sun at one of those focus points. So what we're looking at for the law of ellipses is sometimes the planet is as far as it can be, and sometimes when the planet orbits to the other side, it's as close as it can be. And we have two names for that. We call this aphelion and perihelion. I can write them in there for you if you want. Aphelion. And what we're looking at for the law of ellipses is an equation called eccentricity. It's how elliptical or how oblong or crunched up this orbit is. It's a pretty easy calculation. We say E, I use kind of fancy E to know that it's not energy. We'll get to that next week. We say it's the aphelion minus the perihelion divided by A plus P. So for this lab, it's pretty straightforward. You have some data that you've been crunching for the force of gravity lab. What we're gonna need is to go find these distances for the planets. We'll be doing all of it today. What I want you to do, because we know from this radius the other day, that number can be really big and stupid. So what we're gonna use is an astronomical unit, 1 AU. And when you're looking around and finding the aphelion and perihelion, the AU is the distance from the Earth to the sun on average. So we use that number, one, to get rid of all the exponents and all the scientific notation, but it gives you a perspective of, hang on a second, if this planet is 5 AU, it's 5 times further than the Earth is from the sun. So what you're gonna do is find the A and P of each planet, plug them into the equation. It's pretty straightforward. You should get a little decimal out of here. The closer it is to 0, the more round the orbit is. The closer it is to 1, the more stretched out the orbit becomes. And that's kind of the shapes that we're looking at today. His second law is called the law of area. We're actually not going to calculate it, but I'll show it to you real quick. Essentially, as a planet moves from, let's say, here to here, let's say that takes 3 months. And then over here, it orbits that far, and that also takes 3 months. And what his second law says, the law of equal area, is that this cross section, because the time frame was the same for both, that those areas have to be equal. It's pretty neat, just geometry of it and how fast they're moving. They're moving faster as they get closer because of that force of gravity. But this area is kind of hard to map out without some calculus. So if you're bored on a Saturday, you go for it. We are gonna look at is his last one. It is the law of periods. This is about time. Kind of like the law of area had a time component. What the law of periods says is there is a relationship between period, the time, we use capital T for period, and the distance of the orbit. Now they're not equal. What Kepler found is there's a relationship that the ratio of the time squared to the radius cubed. And he found that this ratio, so if you divide it over and say T squared R cubed, it equaled a constant. Now it turns out for the solar system, this constant is 1. So if this is 1, and if you want to put this equation back together, you just get right back out what we just talked about. So what we're going to do for Kepler's third law, the lab, what we're going to find is the period, the time it takes each of these planets to get around the sun. So there's two ways you can do this. This is why I told you to save your data. You can do it two ways. You can take your radius and you can convert it to AU. You just divide it by the Earth's distance, 150 million. Or you just take your A's and P's, A plus P divided by 2 is also the average radius. Because this is the max, this is the minimum. That's how you find an average. We've done that for velocity, right? So once you have this R, you plug it in, you cube it, take the square root, and it gives you the time. So for Earth, right, Earth has 1 AU. This math is pretty technical here, watch out. We're gonna cube 1, and then take the square root of it. So for Earth, it takes 1 year. So all these answers are gonna be in years. You do have to use AUs for this one. You don't have to use it for eccentricity, but it does make your math a lot easier. But you're gonna be using your data from the other day. You can just convert it, or you can look it up again if you don't wanna do the math, I get it. But we are gonna do the calculations for all 13 planets, 12, excuse me. You won't be doing Earth. Cool.